My name is Maurizio Barbaro. I'm from Red Hat RHEL sustaining team. I'm a senior maintenance engineer there. Today I will short talk you about a vulnerability that's quite common. It's called use after free. Many of you probably already know. And especially I would like to focus your attention on a couple of demos I prepared for you, just to show those known vulnerability in action and to present some of the related topics. This is the agenda for today's session. I have a space for your question and answer. Please keep all your questions to this session at the end, and we'll be happy to answer. Then, use after free vulnerability still remain a serious security threat nowadays, despite is not so young, let's say, and is frequently exploited and brings a lot of issues. Considering the National Institute of Security, the UAF vulnerability is one of the most dangerous, still in the top 10 of their classification. A bit of theory, just to not be too much in details, but what is this UAF free? It's a vulnerability that occurs when a program releases the memory that's obtained by the operating system, but still continue using the memory area after the pointer and the memory was freed. This can lead to a series of issues. You can have program crashes, data corruption, or even arbitrary code execution that could be arise to privilege escalation. We will see later an example of that. As many other security vulnerability, attackers could be aware of the presence of this vulnerability in your application and could try to manipulate the code in order to obtain access to the system, getting data, and so on. Double free is an iteration of the single use after free vulnerability in the sense that the same problem duplicated twice. So the pointer is the memory pointed by the code is freed twice. And this can completely destroy the heap structure the operating system could provide you for the memory allocation. Again, could expose the application to worst consequences. This short animation, I hope, is quite simple, just to give you an idea of what is the exploitation of the vulnerability. The pointer is the memory is deallocated, and the second, the last line of the code, essentially, show how an attacker could copy its own content inside a memory that apparently was freed. But we will see in another demo another effect of that. So essentially, what we can do as a developer to get rid of this, we can try to approach a programming language that's supporting a proper handling of the memory. There are modern languages, there are several ways to do this. For example, some languages have garbage collection, like for example, the Java and others. Other have reference counting mechanism that could reduce the possibility to to have those dangling pointers. There are other borrows checking that are considered at the moment one of the most effective. The problem is that many largely used languages like C, C++ do not have anything basically. They have manual memory management. That means that here the developer are responsible of the memory management. So we have to properly balance allocation and deallocation of the memory and taking memory of who used a region who freed in order to avoid the creation of dangling pointers that essentially the user-free vulnerability is created by dangling pointers, the pointers that still are valid inside the application life, despite the programmers thought to have freed the memory. So another part of the program during the workflow could have access to the previous used memory data. Again, we can have unpredictable behavior, silent corruption, data leaks, or even system crashes. The problem is being correlated to the human nature. We are human, we can forget things, we can forget to properly track pointers. So at the end, it's not that easy to find. So the question is, but can we do anything at the end? Luckily, yes, we can do something. We can at least try to reduce as much as possible. For example, we could use one of the most common techniques, that's setting the pointer to a null value after the memory deallocation. And here I put the sentence and wait for the fireworks. What I mean, most of the languages, whenever we'll try to use this zero-valued pointer, will crash immediately. So we have an immediate indication of the offending line in our code. And at the same time, we will not expose the application to the vulnerability itself. Of course, this is not something that could be think to use in a critical application in field. It's meant essentially for testing. And one of the way, in fact, involve the massive testing with those nullification of the pointer. But another best practice that's related to this, what we can do to mitigate, is to test the pointer before using, in order to prevent a branch of our program in our application that's freed the memory, so we eventually nullified the pointer. In that case, like the really scholastic example, is a way to avoid incurring the vulnerability, because when we discover that the program is trying to access a memory that is not longer valid, instead of continuing the execution, it will, okay, in this case, exit, but we can do many other things. Another way to circumvent this problem could be to redefine the free or the allocation primitives, creating essentially a wrapper that could be combining the operation. The programmer could call this function to deallocate the memory. In the same wrapper function, we could have this nullification of the pointer. And I would also point out that we could also add another step to provide anonymization of the data after the allocation of the buffer. Because, as I was saying before, one of the problems related to the use after free vulnerability when it is exploited could be also to have data loss and confidentiality loss, because imagine that freed memory contains I don't know, sensitive data. The fact that another pointer, another person, another actor could access this memory and could have effect of losing confidentiality. So this wrapper function could combine all the steps. Unfortunately, just to finish this is not covering everything, because the new redefined free function could do not anything in case the programmer copied the original pointer to the memory that's freed. In that case, we could not do that much. But we have other weapon for us. A best way is to try to detect as long as, before in the CI/CD pipeline or some, not too late still, the presence of the error. We have several open source tools that can help in this operation. For example, we can leverage on the CLang and CLang analyzer tool. That's we can statically scan our application, and at the end we will have this report, and the developer could have a lot of information about possible error present in the code. That's indeed important, because the tool is not guarantee that every error is really a true error. But the fact is itself, you have a report, you are thinking about the weakness present in your application, is a guarantee that the programmer could have a look into the code and could be reasonably understand if the line is the threat is present or not. This is a static analysis that requires the application is basically tested offline, let's say. We could also have dynamic analysis detection. We could run our program with Valgrind, for example, that many of you already know. This way to run the program will guarantee in real time that memory-related error will be displayed on the console. And at the end of the program life, we see a report like the other one. So this combine the two is not creating too much overhead, but it some way create overhead in your application. You have to think about a critical application. A third way is to use the sanitized libraries present in the GCC compiler. We can instrument essentially our code, adding these sanitification libraries, and this time the application will be aborted immediately whenever one of the memory errors are identified. That's very good because we are not prone to the error, and it's good for testing. Of course, it's not would be a problem in case of critical application that are impacting. So it's positive from the point of the security vulnerability, because we will avoid to incur in the error. Obviously, we should consider if you had another type of error, because if the critical application is interrupted, you can imagine the effect. And last things on it that may affect the performance of your application. So you can consider. At the end, for our health, the best is the prevention. because when you have the disease, could be not the best moment. The first policy, the best rule to follow is to choose modern language framework, if possible, of course, that embed the instrumentation to take care of those problematics for us. Otherwise, if that's not possible, we try to implement safe programming techniques like the simple example I showed before. For example, we could use this construct of the smart pointer for some languages that's provided, that automatically add some management of the lifetime related to the memory, reducing the attack surface. The best should be to regularly review your code, run these static and dynamic analysis tools, do education and training for the developers. As a side consideration, there is a typical approach in security that can be combined several techniques. You cannot imagine to have one tools fixing everything. You can adopt different tools, different strategies in order to reduce the problem. For example, you could do massive testing with sanitization when you are in the CI/CD pipeline during the testing phase. You could do, for some critical application, can imagine to run them with those additional libraries that could interrupt the execution in case of error. You can leverage on some hardware feature that some modern processors have, like the Intel, some ARM version. It can combine every of those systems, let's say. So far so good. We have the demo time. This section I will want to show you the use after free vulnerability live. The first one is about an application, a very simple application, just to give you the idea, where an administrator execute his application, insert some critical sensitive data, let's say. It's inputting the data. The data is stored in the memory. Now we use the data and things to free the memory, because it's considered is ignoring the fact that the program is affected by this vulnerability. A third actor logging in the same application as a regular user. It will allocate its own content. But given the presence of those vulnerabilities inside the code, when we'll assess its content, it has at the same time, as you can see, part of the content stored by the previous user. That's to give you the idea of the data leaks or the confidentiality loss that could be embedded in. Because completely ignoring the fact the second user can read information that are not allowed or can even modify. Next demo is the one that originated the title of my presentation. Is when the use after free vulnerability combined with other an application combined with the vulnerability present in the kernel, Linux kernel, could bring us a really, really serious risk. Because in this demo, we see the regular user that assessed the system now is able to act as a root. I will repeat. I will represent the demo. As you can see, the process is scheduled, is not belonging to the user, and the regular user assessing the system worked as a root. Why it was happening? Because, as I was saying, this is a combination of the UEF vulnerability in the kernel and the application called by the user that's leverage on the net filter framework. The net filter is basically one of the Linux firewalls that are used. There is an error basically in this framework ending with parameters. So the attacker is able to exploit the vulnerability, adding those wrong parameters on purpose until the system will create a double free into the kernel memory, and the attacker could be able to inject a bash code inside the kernel space instead of the packet, because the net filter, I don't know if you are familiar with, track packets coming from the network in order to apply firewall rules. So there is an interface between the kernel space and the user that decides the rules. The presence of the vulnerability, unlikely, exposed the system, and the attacker that was able to loop into the structure, at the end become root, starting ends root, regular user. I will repeat again the demo just to give you the possibility to see. No, sorry, it's not the one, that one, the other one. Okay. The regular user have to access the system. This vulnerability affected a lot of kernel versions last year, including Debian, Red Hat, and others. The user, a regular user, cannot create anything. After the execution of the attacking code, as you see, the ID now is 0. It's effectively root. You can create a simple file there as root. It's completely invisible to the system. Instead, the last demo show the effectiveness of the patch, because the attacker will do the same operation. This time, the kernel has been patched, and the attacker will fail. So the regular user tries to create a file that is not able to do. It will execute again the code. This time, the attack will fail. To exploit the vulnerability, the requirement is to have access to the system, having the possibility to compile some small C code, or even to execute some script. That's a real concerning, and that should make us thinking about the nasty effect of use after free, because the combination of having a use after free into a critical part of the system, like the kernel, combined to an error in the application interacting to the kernel, could bring the risk in our system. The other short demo, instead we added the information, the loss of confidentiality, but you can have also other risk as a system crash or things like that. How to deal and to try to mitigate the UF is a combination of action. Luckily, some hardware assistance is provided by the hardware vendor, so we can confine in some hardware mechanisms that have low overhead and could track the error live without doing anything in our application. But it could be not largely used because it requires special hardware, and so it's the best to combine all the soft tools we use and to at first think to the possibility and act in consequences. Okay, now if there are any questions, I'm happy to. Please.
So you've talked about address sanitizer and vulnerability. Could you please explain a bit more what's the difference between them?
Yes, somebody is asking about the Valgrind address sanitization I presented before, and asking more details. Thank you for the question. There are two different ways, because the address sanitization is some you can imagine as an add-on that the compiler itself introduces in your code that's able to understand that the memory location used is for a pointer, for example, and track in a special way this variable. The Valgrind instead is a tool that's used for many cases. In that application is leveraging a tool called memcheck that will keep track of how your code is allocating and deallocating the memory in order to alert you whenever something is not properly balanced or is prone to error. The other one, the clang instead, is analyzing statically the code. Instead of Valgrind and GCC are the advantage to be used dynamically. You can run the application, enrich the application, let's say, and see the effect. Instead, with the clang analysis, we have to do offline. You will you scan your code. Based on the report that tool will present to you, we have to manually read the report, get back to your code, and try to fix the error and see if there really, I don't know, a threat, because, for example, is identified into a part of the code that will be never executed, and that could be a good time to remove the code, for example. But the first tool is meant for static analysis, so you can scan your code, get the report, plan the action about what are the findings, and that's it. Valgrind and the sanitization are meant for dynamic, so they will give you immediate information about the presence of the error. Then you should give back to your code because the last two are analyzing the binary code. They will present an information that your program at the line X, Y, or what is presenting a memory leaks or a memory use after free error. The sanitization will abort the execution of the program, so will immediately tell you the line causing the abort. But again, is on the code, on the binary code, so you have to get back to your source code and fix. There are also available some handful plugins that you can add to your favorite editors that could give the information about the presence of vulnerability while you are writing the code. Of course, for the new code you are writing. That's another help you can have. I hope to have answered your question. Yeah.
There is a question online, and the question is, what is the number of the CV shown in example 2 out of 3?
The CV in the example is the 2024 1086. Was a CV that appeared last year. Now the patch is affected many kernel versions. Luckily, it has been patched. And time to time, we have a lot of examples affecting frameworks, application framework. That is instead affecting the kernel, and that's why the effect is really nasty.
Thank you.
Any other question?
Hello, I have a question about the Slang Analyzer tool. How many false positives does it generate?
Good question. This is a good question. And I think it depends a lot of the complexity of your application. And from my experience, every tool is not perfect, as you know. So you can expect to have false positive. And that is, in my opinion, a positive thing in any case. Because, okay, if you have a false positive, you have to investigate on your application. Once you are investigating on your application, you are doing a great job, because you are putting your head that you have to review your code. That could bring you also a collateral positive effect. For example, you can identify other weakness or things like that. So the fact itself to have determined that these are false positive, in my opinion, is a good thing, because you have understood the problem, you have analyzed your code, and you have stated that it's not really an issue for you. About the number, I don't know, cannot honestly give you a number. I think it depends really on the complexity of the application. Any other question?
Hello, thank you for the presentation. I have a question regarding the demo. I'm not sure I get the point. I hope you show the code of the program, which enable us to get to be a root. I don't know. You can explain what was the main part of this program? What the memory was? I understand that it used memory after the free, right?
Yes.
Yeah. What the memory was used in the program, and if do you think there is more bugs in the kernel that enable to, yeah? If probably there is still some more bugs in. So that's my question.
Thank you for the question. For the first part of the question about the memory used, unfortunately we are out of time, but it is essentially the kernel memory where the packets that rule of the firewall are inserted. That's between the kernel and the application creating those rules. And the vulnerability was into the kernel part. By the way, the application had another error inside its parameter handling that could be triggering the kernel vulnerability. So there was a very nasty combination of things, because it was just the vulnerability itself without the external trigger maybe should be there till now without effect. Instead, having those applications that trigger the vulnerability bring us this error. Okay. Thank you for your attention. Good afternoon.